Okay, let's get started. We will talk about the schedule in a moment, but before we do, we're working our way through a section on robotics, and I'm doing my best to explain robotics to you, but perhaps someone who can explain it better is Morgan Freeman. So if you would like to tune in to Japanese national television on this Friday evening, Morgan Freeman will be talking about my research in robotics in Japanese as translated by one of my Japanese colleagues. If you don't have anything better to do this Friday night, there you go. There is also an English version of this. I think if you Google through the wormhole, Morgan Freeman, robots, you'll be able to find it. Okay, so if you don't understand what I'm telling you about robots, go have Morgan explain it to you. Okay, back to the schedule. So we are working our way through our section on looking outward and thinking about classes of technology that will be interacting with the physical environment, not unlike how we interact with the physical environment. We're starting to talk about robots that will move about in the same environment as us. And we are going to finish our discussion of how the fact that you interact with the world influences the way that you think, which is situated embodied cognition. We're going to finish that discussion in the next few minutes. And then we're going to start to move on to HRI, Human-Robot Interaction, not HCI. So we've spent some time talking about how robots, like us, can push against the world and observe how the world pushes back. What happens when robots start to realize that there are certain things out there in the world that also can actively push against the world and push back, which robots are going to call humans. And there are certain ways that robots should interact with these other things called humans, and there are other ways that they should definitely not interact with those other things. That's HRI. We will then, on Friday, talk about a particular research project we have going on in the lab called Twitch Plays Robotics, which brings together some of the stuff we've talked about in terms of robots and also some of the HCI and interface stuff we've been talking about in this course. And that should do it for the week before Thanksgiving. Okay, tonight you have your first weekly report due, and this is you telling us your plans for user testing. We'll talk now a little bit about report 2, which is due not next Wednesday, which is the Thanksgiving recess, but is the following Wednesday. So you have 2 weeks to do report 2. And the reason why is I want you to actually do some user testing over the Thanksgiving break, and you're going to write up the results of that user testing and submit it when we get back on Wednesday, November the 30th. Okay, so report 2 is now up on Blackboard. And again, you're going to be doing some user testing and telling us a little bit about the results. So I want to go through this kind of quickly with you. There's only, 14 page and a half of instructions for this one. Pretty straightforward. So your goal is to recruit 2 people when you're back home for Thanksgiving. Ideally, these are people that have not seen your system before. Maybe these are family or friends that you've told them a little bit about Leap Motion, but they haven't actually seen your system in operation. I want you to try and get as naive a user as possible. And the reason why, obviously, is you're going to learn most from a user who hasn't been influenced by all the other prototypes you've been developing and exposing them to.
One of my friends is hearing impaired and is fluent in sign language, so probably shouldn't test on him.
That's a good question. Why not, right? Let's see how they do. Maybe there's nothing for them to learn.
Yeah, I'm just curious what his feedback will be.
I think that would be perfectly fine. Just include that in the report, and that's fine. That would be great. Okay. So if your user knows sign language already, that's perfectly fine. Okay. So don't forget to take home your Leap Motion and your laptop with you so you can actually test it out on them. Okay. While you're doing your user testing, you're going to be annotating or writing down notes during the interaction. You need to be able to do this very quickly because you're going to be looking at the screen, you're going to be looking at your user, making notes. Is the user looking at the screen? Are they looking at their hand? Are they looking at the Leap Motion? Are they looking at you for confirmation? It's going to go very, very quickly. So I want you to test your user interaction first before you try it out on your 2 guinea pigs over the Thanksgiving break. What I want you to do is to either print out or have an electronic copy of the use case that you're writing for report 1, which is what you think is going to happen. And I want you to also print out your list of metrics so that you can tick off when you actually see the user fall into one of those metrics or one of those things that you're looking for. It doesn't matter to me whether you print it out and tick things off on a piece of paper or whether you have an electronic copy and you're annotating it electronically. Just practice, because again, you're going to have to do this very, very quickly. You don't have time to fidget with your tablet if you're doing it that way as you go. So either paper or electronic is fine. With us, make sure you print out 2 paper or electronic copies of each use case and your metric list, because you're going to be doing this twice with your 2 users. Okay. Before you start, you yourself should create a few synthetic users and do some user testing with it. So you start to bulk up your database a little bit with material, because one of the things your user is going to be seeing as they interact with your system is how their performance compares with other users, right? So you can pretend to be synthetic user number 1, who is not very proficient and takes a while to learn what's happening. You can then create a second synthetic user who already knows sign language or gets the system and starts to learn very quickly. Doesn't matter to us. Again, make sure it's stored in the database before you begin. You may have a fellow member here in the class or a roommate back home who you've already exposed your system to. Practice with a buddy first and have them go through, actually do a dress rehearsal of user testing. So have your friend or colleague sit down, face the screen, make sure you sit so you can see their face and you can see the screen. And for all of your users, you're going to tell them the following, and then hopefully no more. And I won't read all of this, but you're sort of giving them guidelines about what they're going to do. They're going to interact with the system for 5 minutes. About halfway through, you want them to stop or shut down the system and then start the system back up again. So we get some data from their first and their second session. Doesn't matter to me if you stop the system for them and restart them. That part's not too important to me. Doesn't matter. You're telling them that you will observe their interactions, but you will not explicitly help them unless they really, really need it, right? You want to see whether they can, if they do become confused, if they can sort of look at your visualizations and then sort of figure out what they have to do next. Okay. You're going to tell them that they should be trying to do their best to figure out what to do, but if they really get stuck, they can ask. During the session, tell them that you'll be making notes to help them improve the system in future. And when they're done, they can tell you what they liked and what they didn't like. So you don't want your user giving you a running monologue as they go, because you're noting other aspects, right? You're trying to mark down how the interaction is actually going and what they are actually doing. After the fact, they can tell you what they thought worked well and what they think needs improvement. So far, so good? Okay. So start a timer, start up your system, and during your mock user, pretend to mark off the use cases as you go. In the case of the use case, you're ticking off things that actually work, and you want to see where what actually happens with the users diverge from what you think is supposed to happen. Right? So the very beginning of the use case is you turn on the system and it shows a picture of someone's hand hovering over the leap motion device. As long as your system doesn't crash, you're pretty sure that that particular thing is going to happen. The next thing might say you believe that the user will then hover their hand over the device. If your user hovers their hand over the device, tick that one off and on to the next one and keep going and see where things start to diverge. Okay. While you're doing that, you are also ticking off things on your metric list. So things like, you might have a metric like how many times does the user pause and seem not to know what to do next. Right? Now it's up to you to judge whether the user is actually in that state or not. Another metric might be the user tries to shake their hand to undo or reset the system, right? How often does that happen? So you're ticking off those things when they occur. They might happen more than once, so tally them up as you go. And you might also want to try and jot down, if you have time, where in the program are they when they do that, right? So if the user is explicitly shaking their hand to try and reset something, what state was your program in when that happened? You've got to be able to see the screen and know. You probably actually don't want to write down this full text. You probably want to memorize the various states in your program, right? By now you probably have 6, 7, or 8 or 9 separate states to your program. So you might say user shakes hand, S0, meaning they were in state 0. Your program was in S0 when they shook their hand, right? Because you're eventually going to try and take these results and go back to realize what was it, what state was the system in where the user got confused, and how can you improve the visualizations or the interaction in that particular state to make sure your next user is not confused at that point. Are you confused? Oh, so far so good? Okay. Okay, let's see. And then again, write down specific comments when you go. When the user testing is done, I want you can excuse your tester now, I want you to log back in using their account and just get a screen capture of your visualization, right? So we should see the data from that user's interactions, how they compared between their first and second session, how their performance compared to other users. Grab a screenshot of that, and that's going to go into your report, which will be proof to us that your users actually interacted with the system. Okay, now you're ready over Thanksgiving to actually do this for real with your 2 user testers. Do not allow user 1 to watch user 2 and vice versa, right? You want a clean interaction. You want to have a naive user who hasn't seen the system before. You want to see how far they can get in terms of learning ASL by just looking at your screen. Okay. Finally, you're going to be submitting, when this is all over, the Wednesday after Thanksgiving, a single 8-page PDF document. It's going to be made up of 2 sets of 4 pages for the 2 users. Page 1 is the annotated use case, so how far did they get before they diverged from the script. Second page is the annotated metrics list. How many of the metrics that you formulated actually arose during the interaction? Third page is tester comments, what they said about your system. And the 4th page is the screenshot showing what data your system collected from the user. Sound good? Okay, that's what we're looking for in report 2. I want you to keep in mind throughout this process that you're going to be then using this 8-page PDF to figure out how to improve your system for report 3. So the deliverable, what you're going to be submitting at the end of report 3, is what you've improved based on what you observed in user testing. So make sure you take as careful notes as you can during user testing so that you've got very specific ideas about where your system needs to be improved. Sound good? Okay. Okay, so that's report 2. Let's jump back to lecture. So we're talking about robots, and we were talking about this idea of situated cognition and embodied cognition last time. Just to refresh your memory, yes?
I just have a question about the report.
Sure.
When we go to make improvements, it doesn't have to be stuff just tied to the metrics we identified as first.
It doesn't only have to be, but I do want to see that you learn something from user testing, right? So if you submit report 3 and say, well, I just kind of disregarded all the user testing and I just knew where I needed to improve things, that's fine.
Well, I guess I'm asking more about the metrics we're identifying as first report. Because when we do user testing, something new could emerge, not related to the metrics. It's okay that the improvements are based on those new things.
Absolutely, right? So you're in the comments section from the users. The users might say, everything was great, but I'm red-green colorblind. So I was confused because you're telling me in retrospect something got redder, I didn't see it, right? Hopefully there will be some of those unexpected things that come up, right? That's perfectly fine, right? What can you capture in general from user testing that will help you improve your system next time around? Okay. Okay, so back to technologies that are interacting with their environments. Technologies that have a body with which they can push against the world. They have some aspect of embodied cognition. They decide how to push against the world. And if they have sensors with which to directly sense the world, they can sense the repercussions of their actions. So they are also situated in the physical world, not hidden behind a pane of glass, passively waiting for input from a human user. Okay. We put those two things together, and we're going to use this umbrella term, a complete agent, for human, animal, or robot that can push against its world and observe how the world pushes back. We talked about some of the inescapable properties that such an agent has. It's beholden to the laws of physics. It generates sensory stimulation by pushing against the world, and it also obviously influences its world. Okay, we saw a couple examples last time of how a machine can exploit these properties rather than fight against it. It's a lot easier to learn about objects in your environment, obviously, if you can physically manipulate them, than if you have to sit back and wait to receive millions of photographs or hours of YouTube video and try and learn about objects indirectly in that manner. As we're learning, it's possible, but I would argue that machines that learn about Marilyn Monroe or anything else in our world are going to be impoverished compared to machines that can learn about their world by physically interacting with it. Okay, but that remains to be seen. Let's see. We were talking about affordances last time. So even in a virtual world, if you have an avatar and the avatar can push against its environment and observe how the environment pushes back, how can we create these virtual environments? Or if we're talking about augmented reality, where someone is looking out at their world through glasses that layer virtual components on top of the physical world, how could you as an HCI designer advertise affordances for things in a virtual world above and beyond what a user would expect from the physical world, right? If they see a door handle, they're going to reach out with their avatar and do this. So there are things, again, that we can do above and beyond the physical world. And we ended, I think, with this last time. We ended with this example last time of trying to do this. Okay, so just to conclude lecture 21 now, we've introduced this idea of situatedness and embodiedness. And in order to really clarify these ideas, it's worthwhile trying to fill out this 2x2 table with examples of technologies that either are embodied or not and are situated or not. What's an example of a particular class of technology that is both disembodied and non-situated? There are plenty of instances of that technology in this room. Standard computers, right? So they don't have a body. They do in a minimal sense that they can send out a sound, or if it's your smartphone, maybe vibrate a little bit to try and get your attention, but definitely much more impoverished in terms of how we or robots can use their bodies to affect the world. How about situated yet non-embodied? What class of technology would fall into this category? Embedded devices, right? So we've already talked about that. Any sensor out there that is situated in the sense it's directly sensing the environment but has limited ability to act on it. This one's a little trickier. Embodied yet non-situated. So a machine that has a body with which to affect the environment, but has limited or no ability to sense the repercussions of its actions.
You got wind-up toy, maybe?
Wind-up toy would be a great example, right? Other examples? That's sort of mechanical. What about a more sophisticated machine?
Seems like a machine that puts together car parts or something like that.
Exactly. Any industrial robot. These days, most industrial robots are also situated. It's obviously pretty dangerous if you have a complex, strong machine that is acting and not able to sense the repercussions of its actions. But that's okay as long as you move everyone out of the way and make a very controlled environment so that the robot can just very quickly do the same thing over and over and over again without worrying about the repercussions of its actions, right? Industrial robots, wind-up toys, an example of that. And the latter category, of course, includes us, includes most robots these days that can both act and sense the repercussions of their actions, right? So traditional robots, non-embodied and non-situated, embedded devices can sense but not really act. Industrial robots can act but not really sense. And now we're moving into a world that is increasingly populated by robots and avatars, which in physical or virtual environments can act and sense the repercussions of those actions. So far, so good? Okay, so let's move on now to lecture 22. We've been talking a lot about robots interacting with their physical environment. Now let's talk about robots that are going to be acting in very close proximity to humans. And now we have to think very carefully about how the robots are going to establish and maintain an interaction between themselves and these other special things that exist out there in their environments called people. Okay, so how do we get a robot to interact with the world? So I'm going to just redo our cartoon here. We have our robot here, which can act on its environment, A for act, and S for sense the repercussions of its action. Now we're going to introduce humans who are going to be in close proximity to the robots. The robots can interact or act on the humans. That might be a physical interaction, like trying to shake the human's hand or saying something to the human. And the robot knows, quote unquote, or learns over time that particular actions cause particular sensory repercussions, right? So if the robot does this to or with the human, what kind of response is the robot going to get? And if the robot is sufficiently socially aware, the robot knows that the human is doing the same thing. The human is acting on the robot and sensing the repercussions of what the human did to or with the robot. So now we're going to focus on this particular feedback loop and talk about how it's different or more complex than this one. Okay, well, how are we going to start to think about this? If we want to make sure that robots are safe and interact with humans in the ways that humans expect or would like the robots to behave, the easiest way to do is think about this interaction, right? When you put out your hand like this to someone you've never seen before, you have an expectation about what they're going to do back, right? So we're going to walk through in lecture 22 here, kind of the social building blocks, things that most humans, and let's be a little bit culturally specific for a moment, humans in the Western tradition expect when two humans who don't know each other come into close physical proximity to one another. What are some of those obvious social building blocks? One way to think about this is if you interact with a human you've never met before and they don't exhibit these basic building blocks, you're either going to be upset, confused, or walk rapidly away.
Eye contact.
Eye contact, right? Super, super important. A robot that approaches a human and is not making eye contact is going to be scary, is going to be who knows what, right? Eye contact is definitely going to be a big part of it. What else? In order to establish eye contact, the robot is going to have what?
Eyes.
Right? Remember we saw Jibo? Jibo had a pretty simple eye, but it was pretty clear most of the time to be able to tell whether Jibo was trying to maintain eye contact with you or not. If it didn't, that would probably be problematic. Other social building blocks that might be important.
Some form of greeting.
Some form of greeting, right? That's important, yes?
Space around you.
Absolutely, right? So a robot that walks up to less than 1 inch of you is probably, again, going to be problematic. Okay. Lots of ways that the robot can fail in this case, right? So there's probably hundreds of them, right? We're going to focus on just 4 today, which are pretty important. And as we've already mentioned, we're going to start with one of the simplest ones, which is maintaining eye contact. And most of the examples today are going to be drawn from this particular robot. This is Cog, developed back at MIT in the 1990s. Cog was made to be somewhat humanoid. So again, it could, in theory, reach out and shake your hand. It would be relatively clear when Cog is looking at you and so on. Okay. So one of the first social building blocks that was built into Cog is what's known as the Vestibular Ocular Reflex, or VOR. This is a capability that you have that you're doing all the time and you're probably not aware of it, which is as you're moving your head, you maintain your focus on whatever it is that you're looking at. So as the muscles in your neck and trunk twist your head, muscles attached to your eyes turn your eyes in the opposite direction so that your eyes continue to look at what you're looking at. It's very difficult, if you try it, to turn your head and let your eyes turn with your head. What you'll typically do is saccade to different points on the wall up here, perhaps, as you're doing it, but between those saccades, your eye is tracking in the opposite direction. It's very hard for you to cancel out your VOR. Okay. So extremely simple. We just put some gyroscopes into Cog so that Cog can detect the change in angle of its head and send those angles to the motors that control the eyes, and the eyes rotate in the opposite direction. Okay. We want eventually our robot to maintain eye contact with the human. VOR just ensures that the robot, as it's moving its head or even moving its body, that it's continuing to look at the same thing, which may be a human's face or something else. So if the robot is going to then use VOR to try and lock on to a human face and keep looking at that human face as the human moves or the robot moves, what is the robot going to have to be able to recognize? So like human eyes, if the robot has cameras, they're just photons that are falling onto these surfaces. You want to maintain eye contact. How are you going to do it? How are you going to start to do it?
It has to locate their eyes in space.
It has to locate their eyes in space, which is actually not an easy thing to do, because eyes, or faces in general, come in all different shapes and sizes and colors and orientations and so on. The human brain has evolved over the last million years such that human faces are one of the most interesting things in our visual field, right? So we talked about attention back when we were talking about cognitive psychology. Tends to be, if there's a human face in your environment, you will tend to lock onto it unless you explicitly try and look at something else, right? Makes sense. Okay. So, but how does your brain do this? How does your brain find the face or faces in your field of view? Very difficult to do. And unlike BabyBot that we saw last time, we're not going to allow humans to physically interact with humans and faces to figure out what faces are, right? They're going to have to do this visually at a distance. Okay, I think this is the last optical illusion we're going to see in this class. This one is particularly tiring if you look at it for a while. Why am I showing you this optical illusion in a discussion on recognizing human faces? This optical illusion, yep.
How easy it is to mess up the human's interpretation of face.
Exactly. Whatever your brain is doing to try and figure out whether there is a face down here, it's been altered to make it difficult. So this is the human face equivalent of what other optical illusion that we've already seen?
I don't remember the name, but it's the cube.
The cube. This is the human face equivalent of the Necker cube, right? So in the Necker cube, there were two different hypotheses. This face of the cube is closer to you, or this one. Same thing here, right? So this may fall on the periphery of your visual sense. So your brain knows there may be a face down here. So your eyes saccade to focus on this part of my slide. And then they're even closer and they say, well, it looks like there's a face here, but I'm not quite sure. What do your eyes do once they get here?
They jump up and down between the eyes and
Hopefully you can feel your eyes doing that, right? If you kind of relax and look at this, you'll feel your eyes jumping up and down between the eyes and the mouth. Why? This is your brain trying to distinguish between these two hypotheses, right? There's a face at this position or this position. What is your brain trying to do? So let's say your eyes saccade to the top row of eyes here. You say, okay, I see some human eyes. This is starting to look promising. There is a face here. I'm going to saccade. I'm going to make a jump to about here. And if I see a pair of lips there, yes, it's a face. Your eyes saccade here, no dice. There aren't any lips here, so maybe I was wrong. Maybe there isn't a face. But wait a second, there are lips. Maybe there's lips here. Okay, I'm going to start here, and I'm going to jump up here. And I expect that when I saccade up here, I'm going to see a pair of eyes. I don't. I was off by a little bit, so maybe not a face. Wait a second, there's a pair of eyes. So this optical illusion is designed to get to lock your brain into this feedback loop where it's right on the edge of trying to decide whether there is a face or not.
Since it kind of goes against what our perception of a human face is, what if you changed her skin color to blue and I don't know, would it be easier?
It's not as tiring or frustrating, right? Because it's not so much that your brain is making a prediction, which is when I move my eyes to this point, I'm going to see a pair of lips, or vice versa. It's okay. I see a blue skin color, so this is one of those creatures from the Avatar movie, or there was a lot of blue light in the picture when the picture was taken. It's not actively trying to mess up the algorithm your brain is running to recognize faces. You might just decide it's a human with blue body paint on, right? Not quite the same thing. The point of this illusion is that the way you seem to recognize faces is active, right? You're not physically pushing against the face, but you are acting in the simple sense that the muscles in your eyes are moving your eyes, and you're making a prediction about the sensory repercussion of that action. I'm going to see lips or I'm not. And you're just on the edge. This optical illusion gets you just on the edge of supporting or disproving that hypothesis. And I will move on to the next slide because it gets tiring, right? Around and around your brain goes. Okay. So how can we do this for robots? There's been lots of attempts to do this for robots for quite a while. This was one of the state-of-the-art approaches back in 1998. This is no longer the state-of-the-art, but this is a good one to start with because it's relatively intuitive for a human to understand how this works. This is known as the ratio template method because it's going to try and apply a template to different places or a frame to different places in the robot's field of view. And the robot is then going to look at ratios or proportions between light levels to determine whether there is a face inside that frame or not. So here we go. The robot is going to take, for example, this picture, and it's going to create a bounding box and move that bounding box around this picture and ask whether it happens to capture a face inside that bounding box. For each drop of the bounding box, it is then going to break that bounding box into a series of rectangles that you see here. And then within each one of these rectangles, it's going to throw away the color and just use grayscale. And it's going to take the average brightness of the pixels inside that rectangle. The arrows then show predictions that the robot is making about which pair of rectangles should be brighter than other ones. So let's start with the nose here. So this rectangle near the center, if there is a face inside this rectangle, the nose should be more or less inside this rectangle. What can you tell me about the relative brightness of the nose compared to, for example, the right cheek? So we're looking at the average brightness of this rectangle compared to the average brightness of this rectangle. If there is a face inside that box, what would you expect? Which of those two boxes would be brighter than the other one? Have a look at this face. Yep. The nose would tend to be brighter, right? So I picked John Cleese here because you can see that he's got different expressions and he's also in different overall ambient light levels. But if you look carefully, in most cases here, the brightness of the nose may be brighter than the cheek. That maybe is not true in this one, but generally speaking, that's what you would expect. That's what the outward arrows represent. So outward arrows say, I expect the brightness at the base of the arrow to be brighter than the rectangle at the end of the arrow. You'll notice that the box that should be capturing the eyes tend to have a whole bunch of arrows entering that box. What does that mean? The pupils are the darkest part of the face, not just the pupils, but the eye socket, right? The socket itself, again, depending on light levels, tends to be in shadow, more or less. Maybe not in every case. It depends on the facial expression. But generally speaking, this part of your face tends to be darker than this part of your face.
Does that mean if someone had their face painted, a robot wouldn't be able to recognize facial expression?
Depends on how the face is painted, right? Yes, absolutely. If it's something that tends to break a lot of these predictions, you would fool the robot. If it was uniform blue paint, it would probably still get it correct because these relative light levels are still maintained.
How would you overcome that? I mean, humans can recognize when someone has their face painted like a skeleton in Halloween. They know when they're smiling or sad or whatever, but...
Because humans are running something much, much, much more sophisticated than the ratio template algorithm, right? So in this case, in the ratio template algorithm, the robot is making n predictions where n is equal to the number of arrows, right? Which is, I don't know, what is that, 12 or 14 predictions. Your brain is probably making hundreds of thousands, if not millions, of predictions. So even when your face is painted as a skeleton, you might break a quarter of the predictions, but 3/4 are still going to be met. Most state-of-the-art visual recognition algorithms now that capture faces when you're trying to take a picture of someone, they're relying on probably several thousand predictions at this point, not 12 or 14. That's part of the reason why face recognition algorithms are getting better. Okay, but yes, they can definitely still be fooled. Okay. Okay, so here we go. So we're going to make these predictions, and for each of these bounding boxes, every time a prediction is satisfied, like this case here, we get +1 point. So one piece of evidence saying, yes, I think there's a face here. So the arrow remembers the prediction. but the actual brightness in the pair of boxes is actuality, right? So if actuality matches prediction, you get 1 point. If you really can't tell the difference in grayscale values between this pair, 0 points. If actuality breaks your prediction, is the opposite of what you predicted, minus 1 point. So we're going to apply this point system to every arrow within the bounding box. And if the points are above 11, the robot says, yes, I've captured a face inside this bounding box. And if the total number of points is less than 11, the robot says, I don't think there's a face in this bounding box. Why 11? Probably the investigators who ran this experiment found that that was a pretty good balance between the robot seeing faces everywhere, making false positives, and the robot never seeing faces and making false negatives. What if this threshold was higher? So I don't know how many arrows there actually are here. Let's say there's 14 arrows. If the robot had to get 14 out of 14 points, what would be the result of the robot's behavior? Be very picky, right? It would miss faces most of the time. If the threshold was 0, what would the robot tell you? See faces everywhere, right? Okay. Again, an interesting aspect of psychology. We also tend to see faces when they aren't actually there. We also tend to make mistakes from time to time. There's good evolutionary reasons why sometimes you should err on the side of making false positives, believing something is there even though it's not, than making a false negative, believing that there isn't a tiger there when there actually is a tiger there, right? So humans tend to err on the side of false positives than false negatives for very good evolutionary reasons. Okay, that's just an aside. Okay, so I don't think I can play this in the slide. Let me open this up here. Which one is going to open? There we go. Okay, so on your right, you're going to see the raw video feed from a robot running this algorithm. And on the left, you're going to see, obviously, the bounding box among all the bounding boxes that the robot applied that score above 11 points. Okay, so this is trivial, right? This runs on you've seen this on your phone a million times by now when you try and take a picture. Back in 1998, this was state of the art. This was amazing to see in real time a machine able not only to detect a face, but to track that face as the face was moving about. Okay, so again, we want to try and make an algorithm that's robust, right? Faces come in all sorts of shapes and sizes. From my point of view right now, some of you are wearing hats, some of you aren't. Some of you, your faces are partially occluded. Most of you have somewhat upright faces. If you're confused by what I say, you might cock your head to the side, and I need to recognize your face, even if it's not perfectly vertically aligned. What is it about the ratio template algorithm that makes it robust to different overall light levels? So in theory, if we applied the ratio template algorithm to this image, it should capture John Cleese in all 4 cases. Why is it robust to overall light levels?
Because it's like levels are relative.
The levels are relative, right? For a very important reason. Faces appear in different light levels, and overall faces have different light levels depending on skin tone and color, right? We can't set an absolute value. Everything has to be relative, right? Or in this case, ratios, brighter than, darker than, not this bright or that dark. Okay, so it's clear to see how this is robust to light levels. What else is the ratio template algorithm robust to?
Masks or Only have a picture.
It wasn't, right? When they put the face over, when he put the paper plate over his face, didn't work anymore. Or it worked correctly. The robot said there's no longer a face there. Why? Because that plate has a uniform brightness, right? Mostly 0 points. You know there's a face behind that because you have additional social recognition algorithms running. The robot does not. Is it robust to the overall size of the face? So if the face filled 90% of the visual field or just 10% like it does here, is the ratio template algorithm going to catch that? In order to answer my question, what would you need to know? I've left out a couple details here about the ratio template algorithm. Whether it scales the box, right? I told you that it's tiling the box, but the size of the box matters, right? So unfortunately, the ratio template algorithm is very computationally expensive because you need to make a big box, tile it a few times, make the box smaller, tile again, smaller, smaller, smaller. You need to do a huge number of tiles, and for each one of those tiles, you need to perform this computation. Let's say we wanted to make the ratio template algorithm able to recognize my face if I'm like this, or if I'm like this, or if I'm like this. What would we need to change about the algorithm? Rotate the box, right? So it's all about really the bounding box. As long as you're flexible in how you place the box, you should be able to make this algorithm robust to facial recognition, but it's going to take a fair bit of computation to do so. Okay. Okay, so with VOR and recognizing faces, you can now achieve a robot that's able to lock onto faces and maintain eye contact with them pretty well. I had a good friend who was working at MIT when Cog was being developed, and my friend was working on their PhD and would stay late in the lab, and Cog would be sitting off in the corner. Everyone else had gone home. My friend was working on his laptop, and he'd sort of be working, and every once in a while he'd move his head slightly, and Cog would snap its head around and look at him for a couple seconds and then look away. My friend stopped working at the lab late at night for good reason, right? Very, very simple. My friend knew this algorithm down to the bones. He knows exactly what's going on inside. Still freaky, right? Anthropomorphization, we can't help it, right? I'm not alone in the lab. Cog is here too, right? There's something about these social building blocks that pulls on our heartstrings, right? Okay. Okay, let's move on to something that's a little bit more sophisticated, right? Some of these building blocks are pretty simple, but they become pretty sophisticated. Let's have a look at joint attention. This one is pretty important. So most of the time when I'm talking, you're either looking at your laptop, looking at the screen, or maybe looking at me. If you happen to be looking at me and I look over at the screen, most of the time your eyes will saccade to the screen as well. How did you know that I was looking at the screen?
Saw you looking at the screen.
You saw me looking at the screen, but what is it? What are you extracting from my face to tell you that I'm looking at the screen? How do you know that I wasn't trying to draw your attention to this piece of paper on the wall?
Where your eyes are facing.
Where my eyes were facing. We need to be even more specific than that.
The angle of your face.
I don't know. Well, yes, that's true. Probably, in this case, I'm probably moving my face, but if I do this right, I don't need to move my face. Where my pupils move relative to the whites of my eyes, right? So we get very specific about that. You might see that my pupils move to the right side of my eye socket. Are you imitating that? Do you move your pupils to the right side of your eye sockets? No. So joint attention is actually tricky when you start to think about it, right? Your brain is performing a pretty complex calculation. It's determining that I want you to do something. I am pushing against you. I'm trying to get you to do something. You're sensing what I'm trying to do, and you're acting in a way, hopefully, to try and do what I want you to do, which is look at the screen. But you can't simply imitate You can't copy my A. You can't rotate. This isn't an imitation task, right? If I did this and asked you to do this, or you do this with a young child will imitate. Imitation is relatively easy. Joint attention is more tricky. So in this case, the teacher here is looking at this object. The student is looking at the teacher, and the student rotates their eyes differently so that they saccade, and we're now jointly attending or paying attention to the same problem, to the same stimulus. Tricky, right? How do you perform this calculation? How do you know how to roll your eyes in order to focus on the same thing that I'm looking at? Okay, I'll leave that for you to think about. We'll see how a robot does that on Friday. You have a quiz due tonight. You have report 2 due tonight. And I'll see you on Friday. Thank you.